Okay, well, I should say good afternoon, everyone. Before I really get started, the first thing first that I would like to say thank you for staying with us. And myself, my name is Cora. I work in Green Electronic Appliances in Zhuhai, and I'm very nervous to be here because, thank you. Actually, I'm gonna ask for the applause, but thank you very much. And, because this is the first time for me to be here, and the second thing is because I'm bringing our new solutions to here. The new solution, as you can see from this slide, that's our photovoltaic direct drive inverter centrifugal chiller system. We call it a system instead of only a chiller. I'm gonna share with you more in the contents. First thing first, we will answer the questions why we are choosing centrifugal chiller plus the photovoltaic drive. Why we are choosing this. And second, as the follow, that we will go into more deeper about the solution in details, how we make it happen. And after that, in the coming for point 3, as you can see, the technical evaluation, and then the number 4, the comprehension and the system advantages, we're gonna doing it with a real demonstration project. The project is actually built in our factory. And last but not least, again, based on the actual demonstration project, we have some data captured. And we are more than happy to share with you of all the data. Then you can tell how good and how powerful our system is. So let's begin. This is the milestone of green. Why we are seeing the milestone here? As you can tell from the slide, we are actually began. Our innovation started from 2005. And at that time, that's our first centrifugal chiller, and with our own knowledge, property rights in China. And then, as you can tell there, the IPLV is only 6.7, back to 2005. And as year goes by, as innovation is our endless pursuit, it's not only a slogan, but we are actually doing it in the entire grid. Then we keep working on it. So in 2011, as you can tell, we have our first high-speed pneumatic inverter centrifugal chiller, and the IPLV is up to 11.68. So then at this point, we are already the leaders in the market of the efficiency. Then what else can we do to make it even more better? What else? Then this is the solution in 2013. So we have 6 cutting-edge technologies for our centrifugal chillers, and then it helps us to achieve the energy saving up to 40% compared with the traditional central air conditioners. And now we have our aircon ready. Then let's take a look at the photovoltaic industries. This is a graphic that you can tell. Starting from the X, that's the time, and starting from 2000 to 2012, then you will see there is actually a rapid growth of the whole industry of the photovoltaic. And based on that, as we see, that's a trend. And then also, according to the forecast by the JRC, as you can tell from that graphic, they're gonna be the yellow in the middle. As year goes by, it will take in a large percentage then of the whole, the total global energy resources. And it will be covered 24% in 2050. So after that, we will have a first convention. The first convention after that, and plus the transformer, it will help the electricity go back to the public electrical network. This is the traditional way. And when we need to use this solar energy, then we actually going back from here, following this, and then to do it the second conversion from AC to DC, and then from DC to AC again, and getting to the compressor, because we are using a DC compressor. Okay? By these three conventional conversion, then we are facing 6% to 8% energy loss. So in order to save that loss, then we need to find another solution instead of this. Because if we base on that, there will be no any efforts that we should spend on to do the innovations. And this is the second solution. That will be that we just put instead of another conversions, then we will have a stabilizing unit. And then, as you know that because the solar power is actually flexurizing in real time according to the sunrise, right? So we must have something to make sure that the voltage is stable that we can use. At that part, we can actually doing like what you are seeing from in the screen to act as a stabilizer unit. But this solution can only do one way, which means that we can only get the solar directly getting to our chillers, our unit. But think about it this way. There must be always some times that you actually the aircon don't need that much energy, which means that the solar is generating more power than the aircon needs. That if we cannot use that part of power, we are actually losing it. Right? Correct? Yes. And so, in order to make it happen, we are doing things a little bit differently. We don't have the first part of the conventions, and we don't have the stabilizing unit. And we are only keeping the part in the red squared that you are looking at. In the coming slides, we will see more in details and see more in how technically we make it happen. In order to make it happen, then we will have 5 technologies. The first one, that's, as you see, that's our inverter central figure chiller. And the second one is the ternary converting technology. And the coming is the MPPT control. And then we will have our own innovated PAWM in interleaving control. And last but not least, our power generating and consumption integrated management system. For the last one, I'm gonna share with you more in details in the next part. So let's focus on this one first. As I said from previous slide, that we are actually taking out the first converter and also the stabilizer and only keeping these two. And at the same time, we can make sure that the solar power cannot only go into the aircon, but when the aircon, it doesn't need that much of energy, the power can actually flow back to the public power network. This is our first technology. And the second is the ternary converting technology. As you know, the voltage from the solar, it's in time flashing. And then the loading of the air conditioner is changing in real time. And then they're gonna be like the energies from the solar panel or the energies from the public supply, that it might go to go to the aircon in this time, but in the next moment, maybe not. It is not how it requests. So how are we gonna do with this technology? We can make sure that the switch over between the power generation and then the consumptions can less than 10 milliseconds. It's milliseconds, which means that it's according to the voltage, according to the loading of the aircon, that the electricity can actually float to the way that it's supposed to. And the next is the MPPT technology, as we are using a solar. When we are using the solar, we need to check the voltage of the generated by the solar, and then also the power, and then to make a prospect of the next best point of the generating. So that's why the technology is called maximum power point tracking technology. So thanks to this technology, we are actually using the power generated by the solar panel in the very best way and the efficient way. And then we're going to talk about the PAWM interleaving control technology. Maybe a lot of you already know the PWM or AWM. It is just the control of the inverter system. But we are the first one to combine these two together. Because in some area that you are always using the PWM because it helps better. But in the other period that maybe the AWM is better. Just like every coin has two sides. Okay? And in order to make sure that we can have the compressor work at the real time as it's supposed to be. And then we combine these two technology together, which means that part of the period we are actually using the PWM control, and the others we are using the AWM control. And this power generation and consumption in intelligent management technology system also created by grid. Then I would like to share with you into the coming slides by explaining how's the different mode that we work with. The first one is the photovoltaic generating mode, which means that the aircon is actually not asking for any power from the solar. All the energies then generated by the solar will be coming back to the public power supplies. And the second is when there is no solars available, and then you have the loading from the air conditioners, and then you will get the power supplies from the public power supplies. And how about if you have more power from the solar? And then first thing first, then the solar power will get into the air conditioners first to satisfy the loading, and then for the rest, it will get back to the public power supply. And then in the opposite, and then if you have less solar power energy, and then at this time, the power supply will help you, and then it will help you to give back the power to the units to make it work. And last is that all the solar power generated is used by the aircon. So in the coming part, you will see a lot of figures and the data. All this data is building up by the demonstration projects in our factory. And then there are going to be too much data if we need to go through together. So I will sincerely invite you, if you are more interested about all this, how it happens, then you can join us in the booth, in Energy Next booth, then we can have more discussions, okay? And in here, I will only want to highlight some parts about the data. This is all the reports that supporting that we are not actually saying it, but all the data is coming from the text. As you can see from there, the authorization ratio is 99.04%. The dynamic switching time is less than 10 milliseconds. And for the comparison, we are also based on the demonstrations project I just mentioned. And so, based on that, for the investment you are looking at, if you are choosing our solution with the photovoltaic direct drive central figure chillers, you are actually have 10% less compared to the traditional one. That's for the investment, for the equipment. Okay? And here's the data I would like to share. Also based on our demonstrations project, then in here as you can see, we are actually getting the power 831.6 thousand kilowatts per year. And then that's going to be 806.7 thousand RMB saved per year. That's really good data. For sure, for the math, it's going to be too much to share here. So if you really want to know, if you are interested, join us at the booth, okay? Thank you very much.
Thank you.